Valentin Benedetti, and I'm going to tell you about generalized symmetries, Noether currents, and the ABJ anomaly. This is mainly based on recent work with Horacio Cassini and Javier Magan in these three papers, mainly this one here. The other two are more or less filling the gaps of the first one. And the question we want to ask is, when is there a well-defined Noether current for a continuous symmetry in quantum field theory? At first, this question might seem a bit naive, as one would say that Noether theorem asserts the existence of a local conserved current when the action is invariant under a continuous symmetry group. But it's a long-standing question in QFT to determine under what conditions this theorem actually holds.
Valentin, sorry about interrupting. Do you prefer to have questions while you talk, or maybe
if you want to ask questions during the lecture, it's better for me. Yes.
Okay, perfect. Sorry.
So the message can get across better.
Yeah. Yes.
Well, an interesting point is there are non-counterexamples to Noether theorem. In these counterexamples, the main issue is that the Noether currents one can find is not gauge-invariant. This is the case of the duality symmetry in the free Maxwell theory. It's also the case of Weinberg-Witten theorem that, for example, forbids the existence of stress energy tensors for higher spin particles, free half onwards. And it's also the case of the chiral symmetry in the presence of an ABJ anomaly. And there are some other examples. What we want to ask is what is peculiar about the symmetry in these cases, and how is the symmetry implemented in the absence of another current. Our way there, more or less the plan of the talk, I will tell you about generalized symmetries in algebraic quantum field theory. Then we will work out an example that I think is like a motivation for the idea, which is the graviton example. And then I will describe precisely the relation between generalized symmetries and Noether currents. The main idea would be that when the generalized symmetries transform under the action of another group, a symmetry group of the theory, then there cannot be another current for that group. After that, there are two particular cases. The case that the generalized symmetries form a continuum, but is a non-compact group. In that case, I will argue that the theory must be free. And there is another example, which is in which the generalized symmetries form a continuum group that is compact, which I will give you an example of, that is the ABJ anomaly case. So with that in mind, I will tell you what are generalized symmetries and how they arise in the algebraic quantum field theory perspective. This work is previous, before I started the topic, is mainly by Horacio Cassini, Marina Huerta, Javier Magan, and Diego Pontero in this paper here. And the main idea behind algebraic quantum field theory is that one wants to assign to any spacetime region R a von Neumann algebra of observables. Of observables, I mean physical operators, gauge-invariant operators. And by von Neumann, that the double commutant of the algebra recovers the original algebra. There are also some minimals required imposed by quantum field theory on these algebras. The first one is isotonity, which implies that if a region R1 is contained in a region R2, then the algebra of the region R1 must be contained in the algebra of the region R2. And causality, which implies that the algebra of any region must be contained in the commutant of the algebra of the complementary region. This is to secure that operators commute a space-like distance.
Sorry to interrupt you, Valentin. So yes. Just for understanding the notation, because some of us don't know anything about this. This prime that you read here is the commutant, you said?
Yes, all you have an algebra, let's say this AR, of this AR bar, with bar being the complementary region.
Yes.
Then the prime means all operators that commute with that algebra, with all operators in that algebra.
Okay. And when you write it twice, because here for Neumann algebra
means that it's the original one.
That
if I grab one algebra, take all operators that commute with that, and then grab the second one and take all the operators that commute with that, I get the first one algebra back again.
Okay. Thank you.
So there are more requirements we can ask to these algebras in quantum field theory. The first one is Haag duality, which is essentially the saturation of causality, namely that the algebra of a region is the same as the commutant of the algebra of the complementary region. And additivity, which implies that the algebra generated by the algebra of two regions is the algebra of the union of the regions. These properties are not obligatory, but in some ways a bit desirable. We will assume that the algebras associated with topologically trivial regions, such as balls, satisfy all these properties. This is because there are not known counterexamples, except for broken global symmetries, in which cases this can be fixed. And the other example is the one of generalized free fields, which are a bit pathological in other senses from the algebraic point of view. So we also will leave those cases out. So assuming that all these properties hold with balls, what will happen is that they may not hold for regions that are not topologically trivial. And we will say that theories that have this freedom of this property for topological non-trivial region, which implies that there may be one more algebra assigned to one of these topological non-trivial regions, are theories with generalized symmetries. But let me work this out a little bit more. The main idea here is that when we want to assign an algebra to a region that is not topologically trivial, the smallest algebra that we can assign to that region is what we call the additive algebra. That is essentially the algebra one obtains by gluing algebras of small balls together. Here means that the additive algebra is essentially the algebra generated by all the balls that are contained inside the region. This is a choice for the algebra of a region and clearly satisfies additivity. The biggest, this is the smallest algebra we can assign to a region. The biggest one that we can assign is the complement of the smallest one for the complementary region. Namely, this maximal algebra for the region R will be the commutant of the additive algebra of the complementary region. This is the maximal algebra. Being this the biggest and this the smallest, when these two algebras are the same, it's the case that we can only find one algebra to the region that we are looking at. But if they were to be different, there is more than one possible choice, and all those choices are equally good, provided that they satisfied isotonity and causality properly. In these cases, that there's more than one algebra, we will say that the additive algebra is contained in the maximal algebra. So we will be able to write this maximal algebra as the additive algebra and some other non-local operators that, well, the name non-local operator is a name till now, but it's essentially another set of operators that we call A's. We will be able to check in some examples that these operators are not additively generated in the region R, and they are related to Haag duality violations in the region R. To make this a little bit more concrete, let me
Excuse me?
put an example. Yes.
On the previous slide, if you can.
Yes.
Yeah, I was just wondering why on the blue equalities you have that the assignation for topological non-trivial regions can be unambiguous, but why only for topologically non-trivial regions, and why not only for also for topologically trivial regions?
Well, no, you can find problems in topologically trivial regions. The main issue there is that they are not related to the presence of generalized symmetries. That's why we don't want to talk about those cases today. But you could have these ambiguity problems in topologically trivial regions. There are two well-known cases. The first is when you have some spontaneously broken global symmetry. But in that case, this ambiguities appears when you take the orbifold of the symmetry. So going to the bigger theory without the orbifold solves the problem. The other case that have ambiguities for topologically trivial regions is the case of generalized free field. This was analyzed originally by Reren, and it's evident from the point of view of holography. If you take generalized symmetries, generalized free fields that are conformal, then you can look at the holographic dual of the region and see that there is more than one possible assignation to these topologically trivial regions. But so by assuming that we don't have ambiguities in topologically trivial regions for the theories that we are looking at today, we are leaving those two cases out, and we are focusing on the others where the problem comes from generalized symmetries. I don't know if that...
Yeah, that's perfect. Thanks.
Okay. So why this problem appears in theories with generalized symmetries? Let me talk about p-form symmetries. And I will argue that p-form symmetries are related to Haag duality defects. The main idea here is that algebras and regions ambiguities appear for topologically non-trivial regions that have non-trivial homotopy group pi p. And I will understand a p-form symmetry like a theory that has a close but not exact p+1 form observable field F. The case that is more like intuitive is the one of the one form symmetry. You have a close but not exact true form field. And the algebras and regions ambiguities appear for regions with non-trivial homotopy group pi 1, which is essentially ring-like regions. So that's why you will see the ring draw again and again. The main idea here is that these theories that have a closed p+1 forms, that are not exact, means that we can create these non-local operators, but using the Poincaré lemma. The main idea here is that the p+1 form field being closed, by Poincaré lemma, we know that this should be the exterior derivative of a p-form field A. However, this p-form field A may not be an observable field. If this A is an observable, namely its gauge invariant, we will say that this p+1 form is exact in the observable algebra, and therefore it does not generate a p-form symmetry. In this case, the field A is not an observable, then it does not belong to the algebra of the region R, and we can consider F a closed but not exact form field. However, this field A may not belong to the observable algebra, but there is one version of it that it does. Namely, if we take this P-form field A and integrate it over a closed P surface, P of dimension P, we will get by Stokes theorem the integral of f over a P plus 1 dimensional surface. And we can check that this operator is indeed a gauge invariant because it's the integral of gauge invariant operators. However, if we take this surface, p-dimensional surface gamma or delta sigma p plus 1 to be a non-contractible surface in the region we are looking at, we get that these phi fields are non-local operators. The main idea is that to get this phi field as an integral of gauge invariant operators, we have to integrate over this whole surface. However, these fields does not belong to the algebra of our region because they are not in the region. So we cannot think about this phi field as generated by local observable operators in the region. However, we can indeed assign this operator phi to the region because we can think it about of an integral over the boundary of the region. I don't know that if that is clear what these non-local operators are, but essentially these are not the only ones. We can take also all the unitaries that we can define from this phi, namely all the exponential of this phi field. And all of them are not additively generated inside the region R and commute with all operators in the additive algebra of the complementary region. So they can be assigned to the maximal algebra of the region R. An important point to make here is that this notion of non-local operators is region related. For instance, if we take a non-local operator inside the ring, like this one here, it is a non-local inside the algebra of the region R. But if we take the algebra of a bigger ball that contains the region R, then that non-local operator is locally generated. That's because we are including in the algebra all these operators that we left out before. Well, this idea can also be generalized to non-abelian cases, but I will also left that out today. An important point to make is that these non-local operators can be used to define non-local classes. We will understand a non-local class of these operators as taking one representative and multiplying it, but all of the other possible operators inside the additive algebra. And it's possible to check because the algebra must be closed under the product that these non-local classes satisfy diffusion rules. And also an interesting comment is that we can check that if the algebra of a region R that is additive is the same as the maximal algebra, then the same must hold for the complementary region. This is a consequence of the von Neumann double commutant theorem, namely that the double commutant of the algebra recovers the original algebra, and implies that if we have these non-local operators for the region A, for the region R, that we call A, we should also find some non-local operators, let's say B's, for the complementary region, with the A's and B's being non-commuting. So let me do a more clear example, maybe. This is the case of the one-form symmetry in the Maxwell free field theory. we take a Maxwell field in 4 dimensions. We take the action of the free theory. And it has an equation of motion that implies that divergence of F mu nu should be 0. And also the dual field strength, namely the operator we obtain acting with the Levi-Civita tensor over F, is also conserved due to symmetry. Then we have two forms in the theory. One is F and one is the dual of F that define two non-local operators for ring-like regions, which are essentially the magnetic flux and the electric flux. These operators can be exponentiated, and we will get the Wilson loops and the Toff loops. One can compute the commutator between these Wilson and Toff loops. The fastest way to do that is to compute the commutator between the fluxes. There is a famous result for the Maxwell field that if you take the flux defined over some ring R, and then another flux, the electric flux over some ring gamma tilde, that interlocates the ring like this linked, you will get that the commutator is proportional to the linking number between gamma and gamma tilde. And exponentiating this relation, one would get that for linked Wilson loops and Toff loops, the commutation relations are these ones here. If we look at these relations a bit more strongly, we can check that like taking this Toff loop this way or this Wilson loop this way, that the Wilson loops form a group under which the Toff loop are charged, and that the Toff loops form a group under which the Wilson loop are charged. This group will be, each of this group will be an R, and we have then an R2 group of possible Haag duality violations for the region. And one can also find the same problem in the complementary region, because in 4 dimensions, we can assign this Wilson and Toff loop for this non-trivial region that is ring-like and its complement. So we get a group that is R2 times R2. Well, in the Maxwell theory, in 4 dimensions or in any dimensions, we can assign this Wilson and Toff loop to any ball-like region. Like if you take the algebra of a ball, you will have inside all possible Wilson loops and Toff loops. That is unavoidable. But if we consider some ring-like region, then by causality, we cannot have all Wilson and Toff loops in this region and all Wilson and Toff loops in the complementary regions. We have to make a choice to keep the commutative property of the algebras. This is called the choice of Haag-Dirac net. And well, they're essentially canonical choices. One is to assign the maximal algebra to this region and the additive algebra to the complement, or vice versa. Or another popular choice is the Dirac quantization condition. So I think this is a good moment to stop for questions, like if someone wants to ask something. Okay. So now I will tell you about a bit more involved example, which is how to work out these generalized symmetries in the case of the graviton theory. That will serve as motivation for what will come later. The main idea here is that we want to analyze the theory that is obtained by metric perturbations over a Minkowski background. Namely, we will have a spin 2 theory over Minkowski, essentially. And this is done by perturbing the metric in this way. From the Minkowski metric, we add some perturbation, which is small. And we write for this perturbation the Einstein-Hilbert action to quadratic order, which is this one here. A point I would like to make is that it can be generalized to higher order gravities and other theories of gravities, but the basic idea remains essentially the same. The theory has a gauge symmetry, which is given by the action of linearized diffeomorphisms that transforms this perturbation field this way, with this psi being of the same order as the perturbation. So if we want to construct these algebras and region problems for these kind of theories, or in another way, we want to analyze the generalized symmetries of this theory, we need to understand the gauge-invariant phase space. And a good question here is which one is the gauge-invariant operator? And that operator is essentially the Riemann tensor, is the only one. Abelian tensor and combinations of linear tensors, actually. And it satisfies all these properties, namely is antisymmetric in the first two indices and the second two indices. It has an interchange symmetry, namely I can interchange, that's better, these two indices with these two indices, and that's a symmetry. And it holds the first Bianchi identity, which is this one here, the second Bianchi identity. And in this case, the trace is zero, namely the Ricci tensor is zero because of the Einstein equation. So if we combine this second Bianchi identity with the Einstein equation, we get that the Riemann is conserved. It's a concept biform in the sense, biform means that it's a form in these two indices and in these two indices. So we know that the Riemann is essentially conserved on shell, which implies that the exterior derivative of the dual of the Riemann tensor must be zero, namely this one here. And that allows us to understand this theory as a theory which one-form symmetries. The question that remains is what happens with the other two indices that are antisymmetric between them, but symmetric with the other two. And essentially, what the solution to the problem is to consider not the Riemann tensor, but the contractions of the Riemann tensor, which these space-time functions, where these A, B's, C's, and D's are nothing but constants, like simply numbers. And one can check that all these two forms defined from the Riemann tensor are conserved because apart from this property, we have all of this. And that all of them generate proper one-form symmetries. Once one is convinced of this, the more general non-local operator or non-local flux that we can write is this one here. And it's a bit of a generalization of the Maxwell field case, in the sense that if we take the commutator between these flux in some ring gamma tilde and its complementary linked ring, namely this gamma here, the result of the commutator is proportional to the linking number between both surfaces. The only difference is that in this case has these contractions between the constant that define each one of the conserved fields, these A's, B's, C's, and D's. This is because, well, not all of these fluxes do not commute with each other when they are linked. Some of them still commute. This is the case, for instance, if we take the A's here and the B's here, then this will be 0. But if we take a general operator, we get this expression here. So by doing the same analysis of the Maxwell fields, namely exponentiating these fluxes to get the analog of Wilson and Toff loops, we get that these one-form symmetries produce a group of Haag duality violations that are R20 times R20. But what is interesting in this case is that these non-local operators or generalized symmetry operators are charged under the action of spacetime symmetries. For example, if we make a translation, we will assume that the translation is not big enough to change the fact that these two rings might be linked, but is big enough to change the Riemann tensor. Then we will have that the classes change in this very horrible way. The particular form is not important. What's important is that they change under the action of spacetime symmetries. And one could ask,
Valentin,
what is the reason behind that? And for what we will see, it will be related to the fact that the theory of the graviton does not have a well-defined stretch energy tensor. This is because of Weinberg-Witten theorem. So with this idea in mind,
Valentin, may I ask you,
yes,
before you change slide? So you are working in 4D.
4D, yes. You could do this in any dimension, actually. 4D is just for simplicity.
Okay,
yeah.
Yes. So here you say the theory has one-form symmetries producing a group R20 times R20. This 20 comes from the degrees of freedom of the A, B, C, and D?
Exactly, yes.
Okay.
You can count the degrees of freedom, or this is an antisymmetric tensor. This is a vector. This is also an antisymmetric tensor. It all gets 20, yes.
Okay, and depends on the fact that you are in 4D.
Yes, yes. The
Okay.
group will change in other dimensions, yes.
Okay, thank you.
So then what is the generalization of this relation between generalized symmetries and Noether currents? Well, as I told you before, we know examples where Noether theorem does not hold. This is the case of the Maxwell free theory, the duality symmetry. Another example is the one that if you take two Maxwell fields that are free, they don't interact, and you can see that the symmetry of the action is the rotation between these two fields. Namely, you take one gauge field to the other and vice versa. This is a U1 rotation that does not have a well-defined air current. And it's also the Poincaré symmetry for the cases of spin free half onwards particles. An interesting point is that all these theories do have generalized symmetries. So it's interesting to see what is the real relation there. But before that, I will start asking a different question, which is what happens when there is no Noether current? And how is this group symmetry implemented in the absence of a current? That answer is known mainly in the algebraic quantum field theory community. There is a paper from the 86 of Puchnol, Doplicher, and Longo, which state that if we have a theory with a symmetry group G, where the split property holds, I will get back to the split property in a moment, we can always find twist operators that implement the action of the group by conjugation over the algebras of any given region R by conjugation. Namely, we have these twist operators that when they act by conjugation over some operator, if the operator is inside the algebra of a region R, then it acts as group action. And if the operator is outside the algebra of the region R, then it leaves the operator invariant. So this can be interpreted in some sense as a weak version of the Noether theorem, with the strong version being the existence of a current. Its only assumption is essentially the split property, which states that given two commuting algebras, AR and AR bar, the algebra of the complementary region, there is a type 1 factor, let's call it N. This is some technical result, it's not much relevant here, for which the Hilbert space splits. Namely, we can find some other algebra N that contains the algebra AR, and its commutant contains the algebra of the complementary region, for which the Hilbert space splits. This is essentially can be thought geometrically as I think a buffer zone between the two regions. Instead of talking about complementary regions, we talk about some region R as some region R bar that is slightly separated. And this algebra N is essentially an algebra that gets in the middle of this region for R and for R bar. But for this algebra, we know that this Hilbert space splits. This property holds with great generality in quantum field theory. The only requirements are that the degrees of freedom of the theory do not increase too fast in the ultraviolets, namely that our theory does not have a Hagardon temperature, and that the theory satisfies a well-defined time evolution which can be thought as the time-sliced action. This split property, when it holds, allow us to build these twists. There is a standard way to do that, which can be interpreted as acting with group action over the two halves of this Hilbert space that has split it. The main proof of this theorem is essentially showing that these standard twists can be constructed and that they exist when the split property holds. I will not construct them now here, but it's important to keep in mind that they exist.
I'm sorry. Excuse me.
Yes.
The notation HN for the Hilbert space. What do you mean by that? Sorry.
No, what I mean is that when we have this algebra N that contains this original algebra and the commutant contains a complementary algebra, the Hilbert space splits in two. It's more like similar to quantum mechanics. And I call in Hn and Hn prime the two halves of that Hilbert space.
Yeah, okay. Up to that, I'm fine, but I don't quite understand the how it is precisely defined, but probably I should study a little bit of this split property. So please go on. Sorry.
Yes, essentially the difference is that this, from a physical perspective, these algebras AR and AR bar are algebra of two regions in quantum field theory. One will expect they to be a von Neumann factor of type 3-1. That implies that the algebra has infinite entanglements. That's why when you cut the space and try to define an algebra to each one of the regions, you get that the Hilbert space does not split. The main point about the split property is that this algebra N is a little bit different. It's a type 1, which implies that is isomorphical to some Hilbert space. And essentially it's more similar to a quantum mechanical algebra. What you lose by doing that is that it cannot be assigned precisely to the region. This algebra N is not the algebra of this region, but it's the algebra of the region and some other things that are in this buffer zone. So by losing that geometrical interpretation, but not too much because this region is small, you can do this splitting. That's more or less the idea.
Okay, thanks.
So, okay. There is a generalization of this idea here that applies to theories which generalize symmetries, because in the case that there is an ambiguity in the choice of the algebra of a region, as we have seen before, then you can do this splitting for any of the choices that are allowed. For instance, if we take the additive algebra in the two regions, or the maximal algebra in one region, add the additive in another, or any other choice that actually respects causality and the two algebras are originally commuting, we can do this split. And each of one of these splits will give you different standard twist, because it will give you a standard twist for the algebra that you begin with. So, for instance, if I make a choice, I'm start with the maximal algebra in the region R, the maximal algebra being the algebra of all local and non-local operators, and the additive algebra in the complementary region, including only local operators, then what I will get is a standard twist that acts as a group action over all local and non-local operators inside this region. However, if I make the other choice, the additive algebra here, then what I will get is a standard twist that implements group action over local operators, but not over the non-local ones. So this is a subtlety that might be important later. Another important thing is that there is more than one way to build twists. The standard twists are always guaranteed to exist when we have the split property, but we can build twists in some ways that are with me easier to physicists. Namely, for instance, if we have another current that is not gauge invariant, we can define a twist that the integral of this non-gauge invariant current inside the region, and then add some boundary terms to make this charge operator gauge invariant. But it does not require to go through all this construction. Okay. So what happens when we have another current? In the cases that we have another current, we can build a twist similarly of what I was talking about. Namely, the twist for some region R will be the exponential of this localized charge QR, which QR being the integral of the current O inside the region R. This twist being generated by the another current, it will implement the proper group action on all operators that we might include inside the algebra of our region. Namely, it will act with group action over local and non-local operators indistinctively. However, this twist operator can be checked to be additive inside the region R, because it is the integral of local operators. local gauge-invariant operators. So we have a little bit of a contradiction in the sense that this twist will implement the group action over non-local classes, but it's also additive, which implies that it cannot change the non-local class of the operators. It can add some additive content to a non-local operator, but it's not allowed to change the non-local class of the operator. And these two statements can be true together only if the non-local operators are invariant under the group action. So to make the reverse statement, this essentially is a proof that if the non-local classes associated with generalized symmetries are charged under some symmetry group G, then there cannot be another current for such symmetry group. This is essentially the main proof I was talking to you about. And it can be formalized a little bit, but the spirit is this one here. And there are some important aspects about this idea. The first one is that this statement includes Weinberg-Witten theorem, in the sense that we know that IR massless particles of being equal or greater than 1 have emergent one-form symmetries, and which implies that there cannot be a current for internal symmetries in the case of it's been 1 onward. And also we know that IR massless particles of being greater or equal than 3½ have emergent one-form symmetries that are charged under the Poincare group. This is the example of the graviton I talked before, and it can also be applied to higher spin fields and fermionic higher spin fields. And this essentially implies that the theorem here, because the non-local charges are charged under the Poincare group, then there cannot be another current for the Poincare group, which implies that the theory does not have a well-defined stress tensor. This idea also allows to generalize the Weinberg-Witten theorem to any dimension, as the original proof is in S-matrix language in 4 dimensions. There have been some papers that construct particular examples in 5 dimensions or something like that. But I guess this is the proof for any dimension. And it can also be applied to theories that do not have a specific particle contents. For instance, it's applied to interacting CFTs when these CFTs have the appropriate generalized symmetries, of course. An important question is that this theorem indicates that uncharged classes is a necessary condition for the existence of another current. Namely, if we want to find a theory with another current, we need to check that all non-local classes must be invariant under such symmetry. But the question if it is a sufficient condition, namely that if we have a theory that does not have local charges, then we will be able to find that current. We think that this is true and that the reverse of this idea here holds for UV complete theories. Essentially, what we have is a proof that implies that if all the non-local classes are not charged under the action of a group, then one can only find twist operators that implement the symmetry, and that these operators concatenate. Namely, that if we take the twist operators of some region R and the twist operator of some region R1 and glue them together, we get an operator for the union of the regions. What we are missing here is a convergence of these twist operators to a current, and that we would require some UV requirements for instance, that the theory is UV complete. And the last important point is that if the classes of some region R are charged under a continuous group, of course, we would not have another current, but it also implies that because the group is being continuous and the classes transform under the action of that continuous group point-like, then the classes of the region must form a continuum. And we know that non-local operators come in dual pairs. This is the proof I showed you before using von Neumann's double commutant theorem. Then also the classes of the complementary region must form a continuum. This continuum might be a compact group, for example, R times R, which is similar to the case of the Maxwell field or the graviton or other theories. And we will later argue that this non-compact group implies for UV complete theories that they must be free, or at least have a free sector. And there's also the case that this continuum is a compact group. In that case, we get this more complicated group, U1 times Z times U1 times Z. But it's essentially the example of the ABJ anomaly. Or that is at least the only example that we know of. So
Valentin, so your first hour is now gone. What do you think? If you still have, I don't know, more than half an hour to go, maybe we can stop for questions or for coffee or for whatever. If you have a little more to go, we can continue.
I have actually just to work out these two examples. I think it will take like half an hour or something like that. Maybe you want to stop for coffee or something and then we continue.
Yes, maybe we may take questions now, if there are, and then we can have, I don't know, 5 minutes pause, whatever. Yeah. Okay, so we can do this. If people come up with questions, they can write them in the chat or raise their hands. If you want to go, when you will be back, we can take the questions or keep going with the lecture. Okay.
Okay.
So we are convening 5-10 minutes.
Okay, perfect.
Okay. Maybe there are some questions, I don't know. Maybe we can start again. Okay.
Wait, so let me do a little bit of a summary of what happened in the last hour. The main idea is essentially that theories that have p-form symmetries or generalized symmetries understood as the conservation of some p-form field that is closed but not exact in the algebra of physical operators. Is related to ambiguities in the assignation to algebras of topologically non-trivial regions. However, the main result I talk about is essentially that when these generalized symmetries are charged under the action of some other symmetry group, then there cannot be another current implementing that symmetry. In the cases where these classes are charged, because they are charged under a continuous symmetry group, the fact that this group is continuous implies that we should have a continuum of non-commuting dual classes, namely that the non-local classes generated by the generalized symmetry of a region R must form a continuum, and also the classes of the generalized symmetry of the complementary region. We also know that these non-local classes form groups. And there are two particular cases for these continuum groups. One is that they are non-compact, and the other one is that they are compact. I will talk to you about these two cases now. So let me start briefly with the non-compact case, which is perhaps the simpler one. We understand a theory or we'll say that the theory is has a non-compact form symmetry if it has a closed physical, let's say K form, K being some number, field F, and D minus K form field G, D being the space-time dimension, that is also closed and physically. This condition here. This implies that we can define the fluxes of these fields F and G as non-local operators assigned to topologically non-trivial regions. In this case, it will be precisely a region of non-trivial homotopy group pi k, and the complementary region, which is a region with non-trivial homotopy group d minus k. And we will assume for the generalized symmetry to be there, that this flux and this flux do not commute because of properties that we can deform the fluxes a little bit and extend it to infinity. The only possible choice is that the commutator between these fluxes, if they do not commute, is a C number that we will fix to I in the case that the surfaces are simply linked, namely that we have surface I or something like this. So in this case, the Haag duality violating classes are given by the unitaries that are defined from these two fluxes. Is the exponential of phi f and the exponential of phi g. This is essentially analog to the Wilson and Toff loops of the free Maxwell theory. And this forms an R times R group. Namely, if we exponentiate this relation using the Baker-Campbell-Hausdorff formula, we will get that the B's generate a group under which the A's are charged and vice versa. What is interesting is to understand what theories can have these kind of symmetries. And the way we found to do this is to analyze or bootstrap the 2-point functions of these fields F and G. We know that these F and G must be antisymmetric to be form fields. And we also know that they must be conserved. So the only possible structures, or the most general structures one can find for the 2-point functions, except some degenerate cases where there might be some extra terms for specific dimensions, but what I will tell you about also applies to those cases. But essentially, in the most general scenario, what we get is this correlator here for the FF correlator, where we have included a Kalem-Deman function. And this is a polynomial that is quadratic in the momenta, and the rest of the indices are contractions of the metric. The same applies to the Shishi correlator. And the one which is most interesting is the GF correlator. The only possible structure it can have is this one here, where we have not included this Kalem-Lehmann function. This is because it can only be closed on F and closed on G if this Kalem-Lehmann distribution is non-linear, namely if that the theory behaves as massless or this correlator behaves as massless. one can argue that it might be 0 instead of this thing here. That's true, but by assumption, we have put this condition, so this must not be 0. And we have fixed it to 1, so we get this commutator. So what is really interesting about this correlator is that it does not renormalize, and one can analyze the renormalization group flow of these kind of correlators and study carefully the positivity constraints it has over these Galen-Leman functions, especially the cross-correlator constraints on positivity. And the end result, I would not give you the complete proof because it's a bit long and boring, is that the theory that has a non-compact form symmetry, as we have defined it, is either massless and free, or has a massless free sector, which is the case of the Maxwell theory, of the graviton theory that we have talked about before, where these fields that generate the fluxes are essentially F and the dual of F. Or if the theory is interacting, what we know is that this must be UV completed with charges that break down the generalized symmetries. Namely, that the theory, we need to add charges to the theory that destroy this cross-correlator between the fields, and this correlator does not reach the UV. A nice example of this is a theory of neutral electrodynamics. One takes here a gauge field given by F and a fermion field given by phi. I guess I missed the phi here. And we add an interaction that is of higher order in F, and an interaction that is a neutral coupling between the fermion field and the gauge field. We know that this theory has two form fields that are close. One is F, and the other one is this G, with this G being this composite operator here. One can check that these two fields generate a non-compact form symmetry, and this well-defined at a classical level, which implies by this proof that this theory cannot reach the ultraviolet as is. We have to add charges that destroy the conservation of the form fields in the UV completion. So essentially, it's amounts that one should find charges in the UV completion of these neutral electrodynamics. This is more or less the case of the non-compact group. There are other examples of this thing here which are interesting, but I would like to move onwards to the ABJ anomaly case, what I think is more interesting. What I will argue about now is that the ABJ anomaly, or the chiral symmetry in the presence of the ABJ anomaly, is indeed a U1 symmetry without another current. Let me begin focusing on an example, which I think will make things clearer, which is the case of pion electrodynamics. If I take this action given by a kinetic term of a scalar field pi 0, a gauge field, a kinetic term, and then a quasi-topological Weinberg-Witten coupling between this pion field and the gauge field. Essentially, one could have other terms in the derivative of the pion here. The story will remain a little bit the same thing. But the important point is that the equation of motion of this action are these two here. This is for the pion field, and this is for the gauge field. The equation of motion of the pion field is nothing more or can be understood as the ABJ anomaly appearing in this theory as a classical level. Namely, if we write the current or a current as the derivative of this scalar field, then the conservation of this current has the equation of the usual equation of the ABJ anomaly. And then there's a procedure which was famously introduced by Adler some time ago that allows us to redefine this current that has the ABJ anomaly as the conservation law of a current, which is this one here, that is not gauge invariant. Namely, we can still make our current conserve, but we are throwing out a gauge invariance of the current. In this case, we can define the charge integrating this current over the whole Cauchy slice. And assuming that we have fields that vanish as infinity or gauge transformations that vanish as infinity, one can think about this charge Q integrated over the whole spacetime as a well-defined object in the theory because it's gauge invariant. And then we can compute the action of this charge over the canonical variables. So one can aim to a canonical quantization of the theory. The moment associated with the scalar field is the time derivative, is the velocity. And the moment associated to the gauge field is the electric field, as in the Maxwell field, but it's also had this composite term here. These momenta obey canonical relations with the canonical variables, and these commutation relations can be rewritten in terms of electric and magnetic fields, so we understand what's going on in this way. What is interesting is when we go to a picture of electric and magnetic fields, then the electric fields do not commute with each other, and the electric field does not commute with the momenta of the scalar field. This is essentially because the theory is interacting and indeed not free. One can compute the action of this charge using these commutators over the canonical variables, and the result is that it commutes with the electric field and magnetic fields. It also commutes with the momenta of the scalar field, of the pion field, but it shifts the pion by a constant. This action can be exponentiated to an action over only the pion field. And one can check that is indeed a symmetry of the action, that it commutes with the stress tensor, and is a symmetry of the local algebra. Namely, this current on non-gauge invariant current defines a charge that defines a symmetry on his own right. The only peculiarity is, in this case, the absence of another current. The question is, why is this happening? And I will argue that it falls in line with the previous idea of charged non-local classes. The theory, similar to the case of the neutral electrodynamics, has two conserved two-form fields. One is the dual of F, and the other one is this field G, which is a composite also. This one is conserved due to symmetry, as always, and this is conserved because of the gauge field equation of motion. Both of them define fluxes that are non-local on regions with non-trivial homotopy group by one, the same story as before. These fluxes essentially are the flux of the magnetic field for F, and for G, the flux of the momenta associated to the gauge field. The fact that this is the momentum appearing here implies that we can compute the commutator between these two fields for complementary rings, without worrying about the appearing of some ordering ambiguities. And the result is the same as in the Maxwell field, namely when the surfaces are linked, we get a commutator that is I, namely that the commutator is proportional to the linking number. And we can define the most general non-local operator in this theory as a dion. Essentially, the dion being the product of a Wilson and a 't Hooft loop, with the Wilson loop being the exponential of the magnetic flux and the 't Hooft loop being the exponential of the momentum flux. These dion operators obey the fusion rules and commutation relations of a group that is R2 times R2, which is the same one as in the Maxwell field. Namely, up to this point, we are dealing with a theory that has a non-compact form symmetry. But one can check that these dions are charged under the action of this U1 symmetry generated by this non-gauge-invariant current. The action is this one here. Essentially, it's a consequence of the form of this operator here, this G here. Namely, because the G includes this composite term with the pion field, it is shifted by the charge, and the 't Hooft loops picks up a Wilson loop in the transformation. So in some ways, a little bit similar to the Witten effect. So well, the non-local charge is being charged under the action of this chiral U1 symmetry implies and justifies the existence of no NER current for this symmetry. However, the global charge operator is well defined, and the symmetry can be implemented locally by twist operators, and this twist operator can be constructed, and one can check that they implement the symmetry correctly. But a more interesting consequence of this idea is that one is able to recover the anomaly quantization, or the quantization of the ABJ anomaly coefficient from this fact. The argument goes as follows. The pion model is an interacting effective field theory, and it has a non-compact form symmetry, as I showed you before. However, being interacting, we know that the UV completion of this theory will require charges that break down the Haag duality violating sectors from R2 times R2 to a compact group, such as U1 times Z, U1 times Z. This group might feel a bit weird, but it's essentially the group one gets when you add some charge in the theory to a symmetry of this form. This happens in the UV completion of the pion model inside QCD with massless quarks, or in the effective field theory by including the charged pions as an electromagnetic current. And the main idea is that in these cases appears a minimal charge, a minimal electric charge that we'll call here Q0, where Q is essentially the charge appearing in the covariant derivative. This implies that the group R2 times R2 is break to, as I said before, a U1 times Z, where the U1 corresponds to the Wilson loops with Q, the charge of the Wilson loop. Namely, I did not write it here, perhaps it's important. This is the Wilson loop. Q is a Q phi F. So this charge Q of the Wilson loops is restricted to take values between 0 and Q0. And the 't Hooft loops, because of the causalogy requirements, has to take charges that are of the form 2 pi over Q times K, with K being some integer. So this group of Wilson and loops, essentially this one I was talking about before. Now, the anomaly quantization follows from the fact that this U1 of Wilson loops and the U1 of the chiral symmetry that transforms the top loops should be consistent. If we have this parameter lambda, that is essentially the cycle of the chiral U1, and we know that, lambda, that is the parameter of the transformation of the chiral U1, we know that it acts over the charges of the Wilson and the top loops, the symmetry, as this form here. So the cycle of the chiral U1 must to be consistent with the cycle of the Wilson loops, and this action must take these values, with being going from 0 to n q0 squared over 2 pi, with n being some natural number. And once one is convinced that the compatibility between the cycles requires these constraints, and one adds the necessity of the pion having a compactification radius, which in this case can be taken to be 2 pi f pi, this idea can be used to explain the quantization of the anomaly coefficients simply by these group theoretical arguments. Essentially, we know that what is the action of the chiral U1 group over the pion is a shift by mu, and we have fixed the shift of the pion, and we also know what is the U1 cycle relating to the chiral symmetry. So one is able to obtain this relation here for mu, which mu being also the coefficient that appears in the action. So essentially, it can be translated to the current or the ABJ anomaly equation, implying this thing here, which with n being, as I said before, a natural number, so the anomaly has to be quantized. This n is essentially related to the minimal charge of the chiral symmetry in the theory, and in the case of the pion model is 1. A couple of comments are that this idea can be extended to other theories that have ABJ anomalies. One standard example is the case of quantum electrodynamics with massless quarks. Essentially, the commutation relations and the calculation of the symmetry implemented by this non-gauge-invariant current was done by Adler, and it requires the addition of Schwinger terms to the commutators that come from the triangle diagrams. But the conclusion is exactly the same, namely that the action of the chiral symmetry only shifts the fermion fields as one would actually expect it to. One can also check that in that example, the top loop is charged under the action of the chiral symmetry. This is essentially due to the Witten effect. Well, also, there has been a little talk about this ABJ anomaly example in the generalized community lately. But in this setup, one can see that this idea can also be generalized to non-trivial manifolds, as the local quantum physics actually remains unchanged. Namely, I don't know, if you're talking about a compact manifold with non-trivial topology, then one can always look for a region that is inside that manifold where this story is indeed true. So there is no need to invoke a non-invertible symmetry to explain the ABJ anomaly. So let me leave you with some takeaway messages. The first one is that theories with generalized symmetries have Haag duality violations for regions with non-trivial topology. The second one is that if generalized symmetries are charged under the action of a symmetry group, then such symmetry is not implemented by another current. This result includes the Weinberg-Witten theorem. For example, for the graviton, that we have seen that the non-local classes are charged under the Poincare group. And in the absence of the current, the symmetry is implemented by these twist operators. The chiral symmetry in theories with ABJ anomaly can be interpreted as an abelian U1 symmetry without a current. And the fact that the classes are charged and the consistency of the U1 cycles corresponding to the chiral symmetry and the top loops explains the quantization of the anomaly coefficients. And well, that's essentially everything I have to tell you today.
Okay, thank you, Valentin. We virtually flowed, thank you. So, are there any questions? No.
Yes, one small question. I was wondering if you could spend a word on what happens when we have finite groups, both maybe for the generalized symmetry and for the symmetry group.
Sorry, I guess I didn't hear the question correctly. I think my volume was a bit low.
If you can just spend a word on what happens when we have finite groups, both like
okay.
Okay.
Finite groups, yes. Well, in the case of finite groups, you have to replace the notion of this null current, which is a notion over the twist operators. That indeed there are some conditions one can impose over the twist operators, like some further classification. One is that they might be additive. The other one is that they might be complete in the sense that they implement the symmetry over local and non-local operators alike. In the case of finite groups, then of discrete symmetries, I mean, one can see that the existence of the currents is replaced for the existence of this additive complete twist that concatenates, but you cannot find the conversion to the current. Yes.
Okay, just because I'm not sure I've understood the point. Because we have multiple groups playing on. One can be the group of the generalized symmetries, and one is the group of the symmetry group G that we have studied up to now.
Yes, yes.
The finite group case you just mentioned is when the group G is finite.
You mean when the group of the generalized symmetry is discrete?
Well, I was wondering in both cases, but yes.
Okay. Well, yes, the one I told you before is the one of the zero form group, being a discrete finite group. In the case of the generalized symmetries, in the case we are talking about p-form symmetries, the group that we are using, that is not what people sometimes call the group of generalized symmetry, but is the group of all possible Haag duality violations. For the p-form symmetries, is always continuous. Yes, or at least continuous in one side. Like you can get this U1 times set, but only one of the set of the classes is continuous. I don't know if that explains it correctly, but essentially, let me look for it here. When you go back to this setup, which is essentially the one I use for most of the talk, then you see that the group of duality violations is R times R in most cases. One can add charges to break down that to a smaller group, but the smaller group that you can get is a U1 times it, which is continuous in one side and the other one isn't.
Okay, thanks.
If you add more charges, like to wanting to break down the U1 to a set times set, you will get something that is not a well-defined theory, like it's not renormalizable or something like that. But it's not the group that people usually talk about generalized symmetries. It's a different group. It's all Haag duality violations together.
Okay, and maybe if I can, one more really general question: if you have any kind of condition on space-time, like what kind of
No.
method might be? Okay.
Yes, essentially no. That was a little, I go that a little bit fast at the end, but essentially the talk was all about regions in Minkowski spacetime. But this story can be generalized to non-trivial manifolds. The main idea is that because we are talking about subregions of space, you can see that the physics of a subregion that is small enough remains unchanged. You may have some problems if you want to take, I don't know, for example, let's say S2 crosses 1. Then if you want to take a region that is really strange and goes around the non-contractible circle of the manifold, you may have problems or different physics. But if you take a region that is small enough that is contractible in the manifold, the story is the same. Yeah.
Okay, perfect. Thank you.
Any other questions? I guess we can thank the speaker again. And thank you very much for your nice lecture. And
Thank you
so
for
we will
here.
reconvene. Thank you. We will reconvene for the next episode of TH Live. Bye. Thank you,
Bye.
everybody.